Okay, so in this video, we're going to introduce this other algorithm called the QuickSort algorithm. So one thing that's going to be really kind of the key idea behind QuickSort is that in order to do divide and conquer, there are actually lots of possible ways to divide your input up. So merge sort took the approach of evenly dividing it in half each time. So split an array into two subarrays, and we just take the values that happen to be the first n/2 values on the left and the second n/2 values on the right. QuickSort is going to try to be a little bit more intelligent with its partitioning, such that the actual part of dividing is doing a little bit of the sorting work for us. The key idea is to split the values up by value, but small values go into the left partition and large values go into the right partition. So that just by partitioning your values, you're already getting it a little bit more sorted than before. So QuickSort is also going to split your arrays into two arrays, but it's going to roughly separate them into small values and large values. Now, you might be wondering, how do you define which values are small and which values are large? What we do in QuickSort is we pick a pivot, and this pivot is going to be the element that all values less than it go to the left and all values greater than it go to the right. So part of QuickSort is choosing which pivot are you going to use so that you can actually go through and then separate the values based off that pivot. So we partition our values based off the pivot value we just chose. So, oh, whoops, too far. So at a high level glance, QuickSort is going to look kind of similar to merge sort, at least at like the divide and conquer structure, but it's going to be very different in how it actually splits things up. So it starts by choosing a pivot, and we'll come back to how do you choose that pivot. For now, let's just suppose you choose the first value. So you just grab the first value and say, this is my pivot now. Everything that's less goes to the left. Everything that's greater goes to the right. So we pick the pivot 8, and then we partition our array based off that pivot. Just like before, our conquer step is kind of keep recursing until you finally get to those kind of one element lists. That's going to be the same thing. So there's no like extra step we need to do once we get down to this one element step. And then we need to combine these kind of sorted subarrays into one final array. We'll come back and visit each of these components. So starting with dividing, in our recursive case, we need to choose a pivot. It's going to be the element that we're going to use as our separation tool. So again, I said in this part of the video, let's just assume the way we pick the pivot is always the first value. Then we start by kind of oops, I went a little too fast. There we go. We start by scanning through the array and separating them based off if it's less than or greater than our pivot value. So we'd separate the 2, 1, 7, 6 into the left array and 91, 22, 55 into the right array. So this will involve kind of a linear scan over the data to actually go through everything and see is it smaller or larger than the pivot I just chose. And then we recursively partition. So we're going to keep partitioning these subarrays, and we kind of have to keep around the pivot we chose for this so we remember later why this was the value from the list that we chose to be the pivot. But then we also need to partition these subarrays. So we pick the pivot for the left array, and we recursively partition them. And we even go through and actually say pivot, if it's length 2, you still have to pick a pivot, which then kind of gets you into this weird case where one of the sides will be empty because two elements, one will go left, one's the pivot, and there's nothing to go to the right. This is one of the reasons we actually, if you look back at our learning objectives, I didn't tell you that I wanted you to be able to implement QuickSort. I have no doubt that you could implement QuickSort with everything you learned in this class, but there's a lot of details to get right, especially a lot of edge cases to handle. And so we're not going to worry about every tiny little detail here. It's much more important to understand the big idea of what QuickSort's doing and why. So it's picking these pivots and splitting things up. Our base case is going to be once we get to a list of size 1. Now, the reason we go through all of this extra work of splitting things up based by a pivot is you might notice that if you look at all of my base case nodes, all of the ones with one element inside of it, if you look at all of those, then we're going to run into, sorry, I need to fix my mic a little bit because I noticed that my voice levels are dipping just a bit. if you look at all of these length 1 arrays, starting at the 1, and then the 2, and then the 6, 7, 8, 22, 55, 91, reading that from left to right, notice that that just read out in sorted order. And this is not a fluke. The reason we always kind of partition based off pivots is the partitioning step itself is getting us closer and closer to a sorted order. And if we pivot and partition all the way down to the bottom, we'll run into kind of a sorted series of length 1 lists. Oh, I forgot one of them, 22 and 55. So then our combining step is actually basically free, is that we just combine the arrays as we get them back because they're already kind of sorted based off this pivotness. Now you have to be a little bit more careful about planning for kind of where do you put the pivot itself, and it always just comes after the left subarray. And so we can kind of put everything back together, and because we broke things up by value, they're going to come back to us in essentially sorted order, left, then the pivot value, and then everything on the right. So we just have to concatenate these together. So if you look at our pseudocode now for this QuickSort, it has the same base case as before. If it's length 1, we return the list. Otherwise, we need to choose a pivot, which right now I'm just telling you, you always just pick the first element, but we'll talk about strategies for picking that pivot later. And then you find all the values smaller than the pivot. So you partition into smaller values and QuickSort that. And then you partition the larger values and QuickSort that. You now have 2 sorted subarrays, assuming QuickSort works recursively with the power of recursion. And then we just go through and concatenate them together. All the small values followed by the pivot, followed by all the larger values. And that will be a sorted list. So if we look at this full example, 2, 1, 7, 6, I pick 2 as my pivot. I then separate them into the left array, which is just 1, then my pivot, which is 2, and then all the values greater, 7 and 6. Well, I'm done with the 1 and 2, but 7 and 6 need to be partitioned still because we're not in our base case yet. So I pick 7 as my pivot, 6 goes to the left, 7's the pivot, and now I'm kind of at all of these 1 length arrays, so as I'm returning, I just concatenate them together. So I'd say 6 and 7 becomes 6, 7, and then I combine 1, 2, 1 followed by 2 followed by 6 and 7 to get my final array that looks like this. So it's kind of this nice thing where the pivot was smarter so that it actually broke up the values based off value, partially sorting them on the way. And so then our merge step is a lot less work. We don't have to do any of this like fancy following which one's smaller as we merge along like we did with merge sort. So let's try to analyze the runtime of this algorithm. So what is the worst case runtime? Well, I was kind of alluding to that it kind of really depends on what this pivot is, right? We're kind of been assuming that this strategy works because I can pick a pivot that hopefully well divides the data. In some sense, your best case is if the value you picked as your pivot was the median. If you pick the median value, a median is defined as where half the things are less than it and half the things are greater than it. Then you get this nice divide in half property, which gives us that nice kind of n log n runtime. We'll talk about the best case a little bit more in a second. The worst case runtime you can imagine is, well, what if I pick a really bad pivot? What do you think the worst possible pivot to pick would be? Well, it would be either the smallest or the largest value, because then all of the other values would only go onto one side. We don't get a really nice divide and conquer strategy if one of our workers has to do all of the work and the other one does nothing. That's like, instead of divide and conquer, it's like capitalism strategy, right? So our worst case runtime is going to be something like you have to do n-1 work, kind of make a recursive call on something of size n-1, but you also had to do n work to do this partition. That didn't really help you at all because you only decreased the size of the larger problem by 1. And so if we have something like this and we plug this into the tree method, we get that this ends up being an O of n squared runtime. So in the worst case, QuickSort using this pivot strategy can give us this kind of n squared runtime. Now, just as alluding to, in the best case, if you pick the median of each subarray, then you're going to evenly divide the array into its left and right components. And then we get this nice 2 times n over 2 runtime, which is going to give us that n log n, just like with merge sort. Now, it turns out in practice, assuming we have a nice pivot choosing property, which I'll explain how to do that in a second, we're actually going to get something closer to this n log n runtime if you choose your pivot appropriately. Now, it takes a lot of math and proof to get that, so trust me. In practice, you'll see this n log n runtime. However, because you could potentially choose this worst case pivot, it's possible for QuickSort to not actually be that quick, and you'll run into this n squared runtime. But it's not very likely to happen. And so in a lot of places, people do just assume that they're going to get this n log n runtime. But you, now a CSE 373 graduate, know you have to be a little bit careful with QuickSort because sometimes it might be slow. And that may or may not be okay for your application. Now, unfortunately for QuickSort, it's going to not be stable. So because we're doing this kind of pivot strategy where we move things kind of far away from where they started, it's really hard to maintain that stability property. So we're not going to see stability when it comes to QuickSort. What about in place? Well, the algorithm as I described it is not in place because I was kind of describing making new arrays, but it turns out you actually can do this in place with a lot more complications that I'm going to kind of briefly skim through. But it is to get all of the individual details right, you need a full Java program to describe all that. So I can't get every single index exactly right. But before I describe this in-place QuickSort, I wanted to kind of describe the question I've been putting off, which is how do you avoid this worst case? It comes down to choosing a good pivot. If you can find a pivot that evenly divides your values up, then we get this much better n log n behavior. So here are a couple options that we thought of to talk about for how to choose a pivot. You could just do what we just described, which is take the first element, but we saw that that might not work out pretty easily. So maybe what you can do is actually compute the median. And then we'll talk about this other thing called the median of 3, or just pick one at random, maybe. So let's talk about all 4 of these strategies. Well, we just saw that with taking the first element, it's a very fast strategy. Like it's very easy to pick that pivot, right? You just grab the first value. However, it does have this worst case runtime, this n squared behavior. If you have a sorted list, you're going to run into this kind of quadratic runtime, which is not very good. So then you said, okay, well, Hunter, you told me that the best value to pick is the median. Can't I just compute the median? And the answer is yes. Take the array, compute the median, and then use that as your pivot. Unfortunately, computing the median is hard. It's actually easy to compute a median if you have a sorted list, but we need this median in order to sort the list in the first place. There are algorithms to find the median in O of n time that don't require sorting. Google has one called, if you Google QuickSelect, it's used in some implementations of QuickSort, but it's a complicated algorithm. So it has a lot of complications that are added. So it will end up giving you this nice n log n runtime in the end, but the constant factors are huge. So it turns out, even though this is some way like the optimal way, it's actually the worst way because the constant factors are so high in practice that it's not really runnable. Even though you get this like really nice division each time, it's way too much work that just running even your pick the first element will probably finish on most instances faster. Now, one of the things that instead of just computing the whole median, one thing that people generally do is what we call a median of 3. So instead of trying to compute the median of the whole list, because that could be expensive, just compute the median of 3 chosen elements. Take the first, the last, and the middle, and choose the median of those 3 values. And this makes the pivot slightly more content aware, like it's better than just picking the first element, but it won't always pick the smallest or the largest, but it's not a perfect estimate of the median because it might not be anywhere close to the median. Now, worst case, we still might get this n squared, but real world data, this tends to perform really well at. And so we'll actually see that this kind of strategy, this median of 3, is the one that's basically used in all real world implementations because it works well enough. I wanted to mention, because I think it's kind of fun, QuickSort is also one of the first algorithms people study when you think about trying to study randomized algorithms that make random choices during their runtime. There is a randomized quicksort that just picks an element at random to be the pivot. And that sounds weird. You just pick one at random. What if it makes bad choices every time? That's very unlucky or unlikely. Well, it would be unlucky if you made a bad choice every time, but it's very unlikely to happen. And so in expectation, you'll end up with that n log n runtime and you'll also get that nice runtime with a very high probability that approaches 1 as you have more and more elements in your list. And there's one of the nice things about randomized algorithms is that it's really hard to come up with a worst case input because it's making random choices. So it's in some sense your best line of defense from stopping malicious users from coming up with inputs or instances that would hurt your algorithm, make it run too slow. So I just wanted to mention that we're not going to talk about random quicksort because it's really tough to analyze, but this median of first, last, and middle, the median of 3, is kind of what everyone uses because it's a good enough approximation that's still efficient to compute. So now that we kind of have that, I want to talk about a second implementation of QuickSort. So one that uses first this median of 3 strategy and is also going to be in place. So we start with our setup as before. We have our whole array. And the first thing we need to do is, because we're not in our base case, is choose a pivot. Now, the way we choose pivots in median of 3 is we looked at the first, the middle, and the last element, and we choose the median of just those 3 values. So in this case, we ask, is it pivot, pivot, or pivot? And the answer is it's pivot, right? Of course, it's pivot. No, it's 6 because 6 is the median of 0 and 8 and 6. So we use this as our pivot, and we split up the array. Now, to do this in place, we have to be very clever with how we structure our array. Here's the idea. You store your pivot in the first entry. So you kind of swap the first value with the pivot. And then we need to partition the remaining array into our lower half and upper half. And so the idea is we're going to use one of these finger following algorithms, but has very different kind of semantics and what details we follow. So we start with a low pointer and a high pointer, and we kind of move them closer to meet each other until they form all of the values that are less than the pivot or greater than the pivot. So here I say, okay, the things at the beginning of the array after the pivot are going to represent my low values, and the things after that will be my high values. So we start our fingers here and we say, oh, 1 is less than 6, so that's good. 1 actually belongs in my low list, and 8 is greater than 6, so it belongs in my high list. So what I'm going to do is I'm going to move my low pointer and high pointer closer to each other. So each time we find a match of sorts, like when you're looking at a value that belongs in the low bucket, when low is pointing at that, you can increase low by include it in that bucket. And same thing with highs. If you're looking at a value that's higher than your pivot, you could decrease the high pointer, so add it to your high bucket. The same thing here with 4 and 7, we can add both of them and then increase our pointers closer. Now here is where it gets interesting with this kind of in-place quicksort, is when you get to this part where the low pointer is looking at a 9 and the high pointer is looking at a 2, it's looking at cases where 2 does not belong in the high set because it's less than 6, and 9 does not belong in the low set because it's greater than 6, we swap. So we swap the elements here so that they belong on their respective sides, and then we continue this finger tracing algorithm. And there's an additional complication for when the left pointer is pointing to something low, but the right pointer is pointing also to something low, in which case we just increase the low one and keep comparing this kind of high or thing that we're proposing as high until we can finally get a swap or low and high meet. Oh, lots of details there. But eventually, once they kind of meet and we kind of figured out which buckets they belong in, we now have these partition subarrays, which we can then quicksort recursively and do this all over again, but just inside that section of the array that we concern. So between the pivot and low and from high to the end. Very, very complex details, but this is going to work very, very well in practice. Then there's one other huge complication here, which is now that you have these kind of sorted subarrays, doing this in such a way that you can put the pivot back kind of in the middle. So you actually do this before you recurse. So before you recurse on the left and the right, you actually put your pivot at the end of your low section. And that's okay because we haven't sorted the left yet. So when we quicksort the left, everything will be fine. But the meeting point is where the pivot belongs, and we swap that in. And so now we recurse and sort. So all of those details later, we get to our V2, which looks almost exactly the same as V1, except how we choose pivot was going to be this median of 3. So you can really use any of our selection strategies, but we're going to use the median of 3. And then this partition, for this in-place quicksort, we need to do both of the partitions at once in some sense to kind of separate into the left and the right. And the tricky part is kind of knowing where to move the value, the pivot value, to be in the array such it doesn't mess us up. Lots of little details I'm kind of glossing over because my learning objective for today is not that you can implement this from scratch. It's more about just appreciating that this can be done in place. And I really care more about just understanding what these runtimes for quicksort is and why. So we run into the same best and worst case, but we get it to be in place, which is exactly what we want. So with all of that, I can now kind of do an overarching kind of summary of everything we learned. We have learned so many sorting algorithms. We learned selection sort, insertion sort, 2 versions of heap sort, merge sort, and 2 versions of quicksort. So that's lots of algorithms. And you might be wondering, Hunter, why did we just spend 2 days of lecture talking about all of these things when it sounds like merge sort and quicksort work really well? I'm not sure how to choose between them. Now, this is kind of highlighting the point of everything we learned in this class so far is a design decision. There are different tools that solve the same problem, and it's your job as a programmer, as a computer scientist, to decide kind of what you should use based off the situation and why. So take, for example, what sort does Java use? It turns out it actually uses a combination of 3 sorting algorithms. If you're sorting objects, it uses merge sort because it assumes you want stability. If you're sorting like primitives like ints, it uses a quicksort variation. And it turns out for merge sort, they also use a different variation of merge sort, but same idea. And additionally, even funnier, is if your array is reasonably short, which they define as 48 elements, then they just use insertion sort. So you're like, okay, why did we spend all that time learning insertion sort if merge sort and quicksort are just strictly better? Well, Java uses it for small arrays. The reason is constant factors. Merge sort and quicksort are asymptotically better, but they have a lot of setup for them. And so if you have a small array, just running insertion sort on it is going to be way faster because it's small. It has worse asymptotic runtime, but for small inputs, asymptotes don't matter. So the big takeaway, though, is that no single sorting algorithm is the best. They all have different trade-offs. So different sorts have different properties, and you may or may not need those properties based off your application. The best sort is always going to be the one that is suited to your data and to your application. So to give us kind of like one last at a glance overview of everything we just saw, here are all of the categories of sorting algorithms we just learned. They're organized by their kind of strategy for solving them, starting with iterative improvement, then imposing structure using the heap, and then divide and conquer. And here I'm showing kind of also this kind of corresponds to most inefficient to most efficient. And here we learned insertion sort and selection sort in this iterative improvement category. We learned about heap sort and imposing structure, and divide and conquer being merge sort and quicksort, getting this n log n runtime. I also have kind of some bonuses for why each one of these is useful. So insertion sort is simple, stable, has low overhead, low constant factors, and great if the array is already sorted. Selection sort minimizes array writes because you're only doing swaps, you're not doing a bunch of shifts. Otherwise, we generally don't care about selection sort. Heap sort is always great runtimes, and it's also great if it's already sorted. Merge sort is stable, very reliable. It always has the same runtime, but it's not in place, but it is stable. And quicksort is unstable, but can be done in place. And it tends to be that quicksort runs faster than merge sort. It tends to have lower constant factors. However, you can still run into that n squared worst case runtime. So it's always a trade-off here for which one you want to use. Now, if you look at this slide, you might start seeing that there's a pattern. It started with like these n squared runtimes, and then we made it to n log n. And so you might be wondering, are computer scientists currently researching how to make faster sorting algorithms? Like, can we get down to O of n? Is there something faster than n log n? Unfortunately, we cannot do better for comparison-based sorting algorithms. There is a proven, that I was supposed to say lower, I meant to fix it, I'll fix that on the slides before I post. There's a proven lower bound for sorting on comparison-based sorting algorithms. N log n is as low as you can go. The intuition for how this proof works, I can't do this for you, is no matter any type of algorithm that tries to do comparisons between values and determine like which one's less, which one's greater, there is no way to find the right place that this value belongs with fewer than log n comparisons. And so they kind of show that at a minimum, you need to be making log n comparisons for each element, so it will have a minimum of n log n runtime. Now, that is very hand-wavy. I didn't actually prove that for you, but that kind of frees us in some sense. There's nothing better than n log n. Now, I do have to put a bit of disclaimer because every time we talk about this, someone always brings this up. Yes, there are sorting algorithms that are faster than n log n, but they're not comparison-based sorting algorithms. They're these niche algorithms that I described kind of in our first sorting lecture. So they're really cool sorting algorithms that take advantage of other properties of data that can circumvent this n log n barrier. But they're very different and don't work in this very generic setup that comparison-based sorting does. If I had to recommend one that I think you might be interested in, I would look into this radix sort thing. It's really interesting and how it works. We're not going to talk about it, but it's a very popular kind of one of these niche sorting algorithms. And so I have links to some of these other algorithms that we're not going to discuss if you're curious about learning more. Now, the last thing I want to show you before we part ways for this video is kind of just some extra resources to look at how these things work. There are lots and lots of visualizations of how these sorting algorithms work, and they're great resources for you if you're getting kind of confused about how this QuickSort works or how merge sort works. There are lots of kind of visual tools, and there's also dance editions where you can watch people dance out the sorting algorithms. They're really, really fun. So that's all I have for today. In class today, we'll talk, or in the class sessions for today, we'll get practice with merge sort and QuickSort, understanding when to use them, and kind of making sure we understand the big ideas behind them. So hopefully I'll see you all in class.